Welcome to the lecture for section 3.7. By the end of the lesson, you will be expected to graph rational functions, find their domains, horizontal and vertical asymptotes, and this would actually also say, and slant asymptotes. You will also be expected to solve application problems and use arrow notation to describe asymptotes. A rational function is a function that can be written as the quotient of two polynomials, p of x and q of x, where q of x is not equal to 0. And this function looks something like this. P of x is in the numerator, q of x is in the denominator. Let's look at example 1. Example 1, domain and the local behavior of a rational function. If you notice, I wrote some instructions out. We're going to use arrow notation to describe the local behavior of f of x, find its domain, and graph f of x. Here's f of x. It equals 1 over x minus 1. Let's start by looking at where this function is undefined. If you recall, we cannot have a 0 in the denominator of a fraction. So f of x is undefined when x minus 1 equals 0. If we add 1 to both sides, we see that this is undefined when x equals positive 1. So this tells me its domain is the set of all x such that x does not equal 1. It can also be written as negative infinity to 1 with a union, then 1 to infinity. Let's plot some points and then use arrow notation to describe the local behavior of f of x. So x, f of x, all I'm doing is creating a little table for us to use to gather some more information about this function. Take a moment and fill in some of these values on your calculator. I think the easiest one we can start with is 0. If you notice, f of 0 equals 1 over 0 minus 1, which is negative 1. So take a moment and complete the rest of this table on some scratch paper. Please pause the video and complete the rest of this table on some scratch paper. All right, you should have this in front of you now. At negative 3, our output is negative 1/4. If we plug in negative 2 for x, we end up with negative 1/3. If we plug in negative 1 here, we have negative 1/2. Of course, we worked this one out together. This also happens to be which intercept, our x or y intercept. If you said y intercept, you are correct. If you notice here, we are undefined at 1. If we plug in a 1, we will get a 0 in the denominator. This coincides with the domain we found, and the last couple values we found are here. So finally, what is its x-intercept? Well, what do we let equal 0 to find an x-intercept? We let f of x equals 0 to find the x-intercept. So we have 0 equals 1 over x minus 1. Take a moment and look at this. What would you have to do to solve this? We could multiply both sides by x minus 1. That would cancel out our numerator and denominator, but what are you left with? Does this make sense? It doesn't. This tells me that there is definitely no x-intercept. This is a little preview for what we'll see. There is a horizontal asymptote at the line y. There is a horizontal asymptote at the line y equals 0. This is why we have no x-intercept, and we'll get into that later in this section, but consider this a preview. Now let's go ahead and graph our function. Take a moment to draw your axes. All right, as you can see, my x and y axes are now sketched. We know we're undefined at x equals 1. This tells us that there will be a vertical asymptote, which we are going to define next. This is a line that our graph will never cross. Now let's go ahead and plot some points. At -3, we're at about a quarter. At -2, we're at about a third. At -1, we're at a half. At 0, we're at -1. At 2, we're over at 1. And at 3, we are at 1/2. So our graph will look something like this. As you can see, this graph gets infinitely close to this vertical pink line, which is described by x equals 1. And our graph also gets infinitely close without crossing y equals 0 or the x-axis. Let's discuss some definitions so we can better interpret an example like this and more in-depth examples. Definition: vertical asymptotes. A vertical asymptote of a graph is a vertical line x equals a where the graph tends towards positive or negative infinity as the inputs approach a. These are found by setting the factors of the denominator equal to 0. And recall, when you set the factors of the numerator equal to 0, you find the x-intercepts. With that, let's look at example 2. With that, let's look at example 2. Find the vertical asymptotes for f of x equals 2x squared minus 7, quantity divided by x, plus 6 minus x squared. Let's take a moment to rewrite this. This is 2x squared minus 7 in our numerator. We don't have any common factors between 2x squared and -7, so that stays as is. But we can rewrite our denominator. First, let's put the x squared term up front. Next, let's factor this. So if you notice, what I did here in my first step was I factored out a -1 from each term, so the negative x squared became positive, the positive x became negative, and the positive 6 also became negative. Now we can factor our denominator. We end up with x minus 3 and x plus 2. So our vertical asymptotes, if you recall from the definition, are found by setting the factors of the denominator equal to 0. So we can multiply both sides by -1 to get rid of that negative, and we end up with x minus 3 times x plus 2 equals 0. This corresponds with x minus 3 equals 0 and x plus 2 equals 0. So we have x equals 3 and x equals -2. The vertical asymptotes are found, actually located is a better word, are located at x equals 3 and x equals -2. If you wanted to find the x-intercepts of this function, you would set the numerator equal to 0. So you'd have to solve 2x squared minus 7 equals 0. With that, let's turn to the next page of section 3.7's notes. Horizontal and slant asymptotes. A horizontal asymptote of a graph is a horizontal line y equals b, where the graph approaches the line as the inputs increase or decrease without bound. It is found by dividing the leading coefficient of the numerator by the leading coefficient of the denominator. And we have 3 cases. If you are reading through the text, you'll notice these are defined different than in your textbook, but take a moment and compare the 3 cases. You will realize they coincide with the textbook using different language. Case 1, the degree of the numerator is less than the degree of the denominator. Then we have a horizontal asymptote at y equals 0. And remember, if the degree of the numerator is less, this also tells us that the degree of the denominator is greater than the degree of the numerator. That is the language used by your textbook. Case 2, the degree of the numerator is equal to the degree of the denominator. Then we have a horizontal asymptote Now recall, we defined f of x as p of x over q of x. So our horizontal asymptote is y equals a sub p over a sub q. This is the degree. This is the leading coefficient of the numerator p sub x. This is the leading coefficient of the denominator, q of x. Finally, we have case 3. The degree of the numerator is greater than the degree of the denominator. Then we have a slant asymptote. This asymptote can be found using long division. Well, it can be found using polynomial division. And note that if the degree of the numerator is greater than the degree of the denominator, that tells us that the degree of the denominator is less than the degree of the numerator. And this is the language your textbook uses. Let's look at example 3. Identifying asymptotes. Let's identify the non-vertical asymptotes of each rational function below. So for now, because I want us to get used to the rules that we just learned above regarding horizontal and slant asymptotes, we are going to ignore any vertical asymptotes. It would be a good exercise to independently try to find the vertical asymptotes for each of these rational functions. So let's start with part A. F of x equals 3x squared minus x divided by x plus 2. The degree of the numerator is 2. The degree of the denominator is 1. So which case are we in? The degree of the numerator is 2. The degree of the denominator is 1. If you said case 3, you're correct. So let's divide 3x squared minus x by x plus 2. In order to do this, we write negative 2 on the outside of our synthetic division setup, and inside we write the coefficients only of 3x squared minus x plus 0. We could write this as a plus 0. We know that negative 3 comes straight down. Negative 2 times positive 3 is negative 6. This leaves me with negative 1 plus negative 6 is negative 7. Negative 2 times negative 7 is positive 14. And I have a remainder of 14. My slant asymptote can be described with these first two terms. So my slant asymptote is located at y equals 3x minus 7. Let's look at example B. We have g of x equals 8x squared minus 4x divided by 4x squared plus 3. The degree of the numerator is 2. The degree of the denominator is also 2. Which case are we in right now? If you said case 2, you're correct. This means we have a horizontal asymptote located at y equals a sub p over a sub q, where this a sub p is the degree, where this a sub p is the coefficient, the leading coefficient of the numerator, so that would be our 8. And a sub q is the leading coefficient of the denominator, which is 4. This gives us 2. The horizontal asymptote is located at x equals 2. Let's look at example C. We have h of x equals 4x squared minus 2x plus 1. Let's look at example C. H of x equals 4x squared minus 2x plus 1 divided by x plus 1. The degree of the numerator is 2. The degree of the denominator is 1. What case are we in? We're in the case in which the degree of the numerator is greater than the degree of the denominator, which can also be worded as the case where the degree of the denominator is less than the degree of the numerator. So on our notes, this is case 3. This tells me we have a slant asymptote. So let's set up our long division again. we end up with a slant asymptote here. So the slant asymptote is located at y equals 4x minus 6. Finally, let's look at example D. M of x equals 2x minus 7 divided by x squared plus 4x minus 5. The degree of the numerator is 1. The degree of the denominator is 2. We're in the case where the degree of the numerator is less than the degree of the denominator. This can also be worded as the degree of the denominator is greater than the degree of the numerator. What case is this? If you said case 1, you're correct. That means our horizontal asymptote is located at y equals 0. With that, turn to the last page of section 3.7 so we can discuss removable discontinuities. A removable discontinuity occurs in the graph of a rational function at x equals a if x minus a is a factor of both the numerator and the denominator. So let's take a look at example 4. Find any asymptotes and removable discontinuities for f of x equals x plus 5 quantity divided by x squared minus 25. This can be rewritten as x plus 5, x minus 5 in the denominator. You should be familiar with the difference of squares by now, which we have here in our denominator. If you notice, we have a common factor of x plus 5 in the numerator and the denominator. So this becomes x plus 5 divided by x plus 5 times 1 over x minus 5. This is just 1. So we end up with 1 over x minus 5. This tells me we have a removable discontinuity at x equals negative 5, since x plus 5 is a factor of the numerator and the denominator. What about our horizontal asymptotes? Do we have any horizontal asymptotes? Well, the degree of the numerator is greater than or less than the degree of the denominator. Is less than the degree of the denominator. This tells me we have a horizontal asymptote. At y equals 0. Finally, let's look for any vertical asymptotes. A vertical asymptote occurs when the denominator equals 0. So let's solve our denominator. And let's use this version. If we use this version, we'll incorrectly identify this as one of the factors of the denominator. But we've already counted this in a we've already counted this towards our removable discontinuity, so it is no longer going to make up an asymptote. So we have x minus 5 equals 0, which tells me there is an asymptote at x equals positive 5. With that, let's look at the last example. Example 5. Find the x and y intercepts of g of x equals x minus 1 times x plus 3, quantity divided by x plus 2, 3x plus 2, x plus 1. To find our x intercepts, set the factors of the numerator equal to 0. In case you're wondering why we do that, let's suppose, and don't do this on your own paper, let's suppose I let this entire function equal 0. My very first step is going to be multiplying both sides by this denominator, which will leave me with just x minus 1 times x plus 3 equal to 0. So this means our x-intercepts are located at 0. This tells us to find our x-intercepts, we have to solve x equals. In order to find our x-intercepts, we need to solve 0 equals x minus 1, x plus 3. This tells me that x minus 1 equals 0 and x plus 3 equals 0. So x equals 1 and x equals negative 3. This corresponds to the intercept of 1 comma 0. This corresponds to the intercept of negative 3 comma 0. What about any y-intercepts? To find the y-intercepts, let x equals 0 and evaluate g of 0. This gives me 0 plus 2, 3 times 0 plus 2, 0 plus 1 in the denominator. In my numerator, I have 0 minus 1 and 0 plus 3. So I have negative 1 times 3 divided by 2 times 2 times 1, so negative 3 over 4. This corresponds to the y-intercept of 0 comma negative 3 over 4. And this concludes our lecture for section 3.7.